Welcome to this session. This session, we are going to study about unitary matrices. And this is a definition. So square matrix A is said to be unitary if this condition is satisfied. That if you take A times A power theta is the same as A power theta times A, and you get an identity matrix. And remember, A power theta is the same as the transpose of the conjugate of the matrix A. That's the definition. So now there's a theorem that if a matrix A is unitary, then its transport is also unitary. Now let's quickly prove this theorem. Now, A power theta equals to A theta times A equals to I, since A is unitary, or this simply from definition. So that's what we have, because the theorem already assured that the matrix A is unitary. So A times A theta is the same as A theta times A, the same as I. Now, let me call this one equation 1. Applying power theta on 1, we have A power theta equals to A theta equals to I power theta. So we have not interfered with the equation by doing that, i.e. A power theta equals to A power theta equals to I, since I power theta is just the same as I. Remember, I is the identity matrix. Now we know that from previous result, we know that if we have A, B power theta is the same as B power theta, A power theta. So you raise the product of two matrices AB to power theta. So it's the same as changing the order and then raising to power theta. So therefore, this result would be A theta power theta times A power theta equals, this one is A power theta, and then times A power theta raised power theta should give us an identity matrix. Now we also know that A power theta is given by A. So this will be A and then A power theta equals A power theta A equals to the identity matrix. Now, call this one 2. Applying transpose to 2, we have a power theta transpose equals to a power theta times a transpose equals to I transpose. And then this is the same result as saying a transpose a power theta transpose equals to a power theta times a transpose equals to just identity matrix, since identity matrix transpose is the same as the identity matrix itself. Now we know that if I have product of two matrices A, B, if you get the transpose of the product the same as B transpose A transpose. So this result will be A power theta transpose A transpose equals to A power theta transpose A transpose. Okay, so this would be now A transpose the second equality will be A transpose and then A power theta transpose equals to I. That's by definition from that. So this can be written as A transpose power theta times A transpose equals A transpose A transpose power theta equals to I, which is a definition that A transpose is unitary. So that is how we prove that result. And then another theorem, so we can prove if A is unitary, then the inverse of A is also unitary. You can follow the same arguments to argue that. And another theorem, if A and B are two unitary matrices, then AB is also unitary. So similar arguments of products and raising to power theta can be used to prove those results. So let's do an example here. Prove that this matrix given by 1/3, 1 plus I, 1 minus I, and minus 1 is unitary. Remember, the proof can easily be given if you know the definition of a unitary matrix. So solution, we need to prove that A times A power theta is the same as A power theta times A is the same as an identity matrix. So the first thing, let's get the A conjugate first. The conjugate will be given by 1 minus I, 1 plus I, then minus 1, which implies that A power theta will be, transpose of this will be 1 minus I, and then over 1/3, 1 plus I minus 1. So that is the A power theta. So let's get the product now. A times A power theta will be 1/3, 1 plus I, 1 minus I minus 1 times 1/3, 1 plus I, 1 minus I, and minus 1. And you see this, you factor out the scalars, so it'll be 1/3 because √3 times √3 is 3. And then we have 1 plus I, 1 minus I minus 1 multiplied by 1 plus I minus 1 minus I, and then minus 1. So that's what we have. So this is the normal multiplication. So A times A power theta will be 1/3. Now this by this is 1 plus this times this one is a difference of 2 squares. So when we have 1 plus I times 1 minus I, is like 1 squared minus I squared. So 1 squared is 1, this minus I squared, so plus 1. So this will give us 1 plus 1 is 2. Element here will be 1 times this, so we have 1 plus I. This time this will give us -1 I. This by this will give us 1 minus I. This by this will be -1 plus I. This by this, a difference of 2 squares, so still gives us 2. This by this is +1. So this will be a third into 3, and then 0, 0, 3, and this is 1, 0, 0, 1. So that's one way The other way is to show that A power theta times A can also reduce to the identity matrix. So we'll have 1 over root 3. This is 1 plus I, 1 minus I minus 1 times 1 over root 3 into 1 plus I, 1 minus I minus 1. So this is the same as 1 over 3, and we have 1 plus I, 1 minus I, and then minus 1 times 1 plus I, 1 minus I minus 1. And this is not difficult to show that actually the same structure, and will reduce to 1, 0, 0, 1. So this is an identity matrix. Hence, A is unitary. So that's how we show that. And then example 2, which you can do as an exercise. If you have A given by 1 plus I over 2 minus 1 plus I over 2 minus 1 plus I over 2, 1 minus I over 2, show that A is unitary. So this is what you have to do. The first thing you have to show that you have to get the conjugate, which will be 1 minus I over 2 minus 1 minus I over 2, 1 minus I over 2, 1 plus I over 2, which shows that the A power theta is the transpose of this, which is 1 minus I over 2, and then 1 minus I over 2, minus 1 minus I over 2, and then 1 plus I over 2. Show that if you take this A times this A theta, you get an identity matrix. And the same thing is when you change the order. So A is unitary. Thank you.